Hello and welcome. Today we're diving into the world of big O notation. Big O notation is all about understanding how the efficiency of an algorithm changes as the amount of data it processes grows. It's a mathematical way to describe the upper bound of an algorithm's time or space complexity. In simpler terms, it tells us the worst-case scenario for how long an algorithm might take to run or how much memory it might use. Now the question arises, why should you care about big O notation? Well, first, it allows us to compare the efficiency of different algorithms designed to solve the same problem. Imagine you have two different ways to sort a list of numbers. Big O notation can help you determine which method will perform better as the list gets longer. Second, it helps in scalability prediction. It helps us predict how algorithms will perform as the input size grows. This is crucial when dealing with large datasets or when designing applications that need to handle a lot of traffic. Let's explore some common growth rates you'll encounter when working with big O notation. We have constant time denoted as big O of 1. Then we have logarithmic time denoted as big O of log n. Next is linear time written as big O of n. After that is quadratic time, notated as big O of n squared. And finally we have exponential time denoted as big O of 2 to the power of n. Algorithms with constant and logarithmic time complexities are generally considered excellent. Linear time algorithms are good. Quadratic time algorithms are fair. And exponential time algorithms are poor. Let's start with big O of 1 or constant time. Imagine an algorithm whose execution time remains the same, no matter how much data you give it. That's constant time. For example, consider a function getFirstElement that returns the first element in an array. The time it takes to find the first element does not change irrespective of how large the array is. Similarly, consider another function getArrayLength that returns the length of an array. Regardless of the size of the array, finding its length will always take the same amount of time. Next up, let's understand big O of n or linear time. An algorithm is said to be linear time if the execution time grows linearly with the input size. For instance, think about a function findElement that searches for a specific element in an array. In the worst case, we might have to look at every single element in the array to find the target element. As the size of the array increases, the amount of time it takes to find the element also increases proportionally. Now let's consider big O of n squared, or quadratic time. This often happens when you have nested loops, where you're iterating over the data multiple times. Imagine you have a function called BubbleSort that sorts an array. BubbleSort repeatedly steps through the list, compares adjacent elements and swaps them in the correct order. For an array of n elements, BubbleSort will require n squared operations. Now let's take a look at big O of log n or logarithmic time. Logarithmic time algorithms are very efficient, especially when dealing with large datasets. A common example is binary search. Imagine you have a sorted array, and you want to find a specific element. Instead of looking at each element one by one, we repeatedly divide the search interval in half. If the target element is less than the middle element, then we search the left half. Otherwise, we search the right half. This divide and conquer approach drastically reduces the search space with each step. So let's summarize the key takeaways. Always focus on the worst case. Big O notation describes the upper bound of algorithm performance, which means we're primarily concerned with how an algorithm behaves in the most challenging scenarios. And remember, scalability matters. Choose algorithms that scale well with large inputs, ensuring your code remains efficient and responsive as your data grows. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.